and implement. Yeah.
Exactly. Yeah.
Yeah, makes sense. Thanks.
Yeah.
Sure.
Yeah. Sure.
So yeah, I'm just like making the session go live on YouTube, so it should be live any minute. And I'm also hitting the record button so that if in case the live sharing doesn't work, record on the cloud. All right, so let's actually kick the session off. Welcome everyone. We've got about 30 people. If you're not speaking, if you're not presenting, please be on mute. By default, it actually starts with mute, but just do that. This session is like a regular weekly deep dive session on some algorithms concepts. SD skills has been in flight for almost 10 years at this point of time. And over the last 6 months, we've been a lot more active, especially given all this COVID and tough times. We've converted most of our sessions to online sessions, and that essentially has also increased participation. If you haven't done so already, please join our Slack group, which is sdeskills.com/Slack. Our YouTube channel has a bunch of these recordings, so you can look at the past ones as well. And one other thing I always keep repeating is the best way to learn is to teach. So use this forum as an opportunity for you to step up and discuss some of these complex concepts. Most of us who are actually presenting are not really experts in the subject. We've kind of done a little bit of research. We know most of the concepts primarily because we've kind of read it in the recent past. And we so totally welcome any discussions. And if you have like a better way of doing something, please join and share. So this is like essentially a group where we are helping each other learn. It's fairly a safe space. So, but with all that said, I'd love to hand the mic over to Dippy and Shashank. You can take it away. It's streaming on YouTube, and I'm also recording.
Okay. Thanks, Vivek. So hi, everyone. Dippy here. And today, me and Shashank will go over these typical shortest path problems on graphs. And we have a certain like a flow we are planning to go with. So we'll start with the intuition of these algorithms. And to me personally, this helps, like when a new problem comes up, how do I identify what to apply? And then we'll see how they kind of descend from breadth first search. So we'll talk about the high level intuition behind that, and then going into algorithm, complexity analysis. We'll also go into a walkthrough. We also have a walkthrough of an example, which really elucidates how Dijkstra or A-star works. And then we have 2 questions on these algorithms from Leecode. And yeah, so that's the plan. And we'll see how much we can cover in this time. Yeah, so let me share my screen here. So feel free to jump in with any questions. Can you all see my screen here?
Yes.
Okay. So starting with Dijkstra, right? Since we're talking about shortest path algorithm, the one thing that comes to mind is a simple classic BFS, right? Because it gives us shortest path given a source and target. So a simple graph as the one that I'm showing on screen. So if you're given, this is kind of a trivial example, but it will help us understand the concept for Dijkstra. So if I'm given a source node A and target node D, I'm sorry, somebody has a question.
Yeah, don't worry about the chat,
Okay.
Dippy. I can follow up on the chat and give you like any comments there.
Okay.
Hey, just one quick thing to start with, right? Just from a pronunciation thing, right? So we call it, I think it's Dijkstra usually. The J is like, you know, Y-ish. So it's Dike as in Dikestra. Easier to pronounce that way.
Okay, perfect. Thanks. So yeah, so in this case, if we follow the classical BFS and you're given a source A and destination D, then the path is direct one, A to D, right? And that happens because now there is another path A, B, C, and D, but BFS will give us A to D because it's the closest one in terms of number of hops. And that works because if you think about, we are actually focusing only on the steps, and we are assuming that the edges are non-weighted. So each of the edge, like the cost of going from A to D and A to B or any other path, direct path, is equal. So all that remains is the number of steps or number of hops. So this is all good in terms of BFS. But now if I start assigning weights, right? So do I have a text here? So let me just type here. So maybe I can just.
Do you want to use any whiteboard apps?
Yeah, I just didn't have a graph there, but
Okay.
I can use that actually. Yeah. So we had these nodes here. That scribble thing. Yeah. So let's now if we start assigning weights to the edges. So if I say this is like 100 and just doing some random stuff here. And you can clearly see that the moment we assign weights to edges, the picture changes. In this case, now the shortest path is A to B, C, and D, right? And that's the main use case of Dijkstra, that it gives you the shortest path to a given node or to all the, starting from a source node to all the other nodes in the graph or to a particular node. Provided that, given that the cost of going from one node to another is not the same throughout the graph. So it takes that into account. And how it does that is, it kinds of, let me see if I, yeah, so if you think about BFS, right, the way we approach that algorithm is we go level by level. And if you're starting from the top level, and from there, you only look at the nodes in its immediate neighbors, right? So if you have, in this case, you're only going to look at D and B, right? And the moment you hit D, that's your destination, and BFS reports the path. But in case of Dijkstra, the idea is that you want to look at the path which is best at any given time, right? And yeah, and you want to prioritize your path based on the edge weights. So if you look at it start from A and you look at D and B, in this case, you are going to pick B. Yeah.
Your audio is chopping out. I don't know how we can.
Oh, give me. Sorry, let me just plug in the headphones.
Yep.
Sorry.
Yeah. You're back, but I think it's more network issue than
yeah, let me plug in the headphones.
Maybe the overall network. I hear your voice also, Vivek, is little slow or breaking.
I see.
Sorry guys, give me just 1 second.
Yeah, let's keep going, and we can keep figuring out how to.
Yeah, it looks like few people are able to hear properly. Maybe a few of us, there is some network issue. Yeah.
Okay. All right. Let's keep moving, and yeah, if you guys are not able to hear, just do mention on the chat, and we can probably repeat some aspects of it as we go. Thank you.
Yeah. Is it any better now? Can you guys hear me?
Yeah,
Dippy,
it's
I
good
think
to
you
go.
are good. You can go ahead, yeah.
Yes.
Okay. So yeah, let me know if it's any, if it's really an issue there. So yeah, I was at the point where I was saying that in Dijkstra, we are going to start from A and we are going to find the node with the lowest cost, right? Which is B here. And when we get to B, from there, in a typical BFS, you're only going to look at its neighbors, which is only C here. But in case of Dijkstra, you are going to actually look at all the nodes which are unexplored and in your open list right now, which are D, right, from the previous iteration. And now you have B to C, which is 12. So again, you're going to pick the least cost, which is 12. I'm just giving a very high level idea. We are going to go over the exact algorithm and see how it works. But the intuition is that you're going to pick the path that is the best at any given time and not just the immediate neighbors or the nodes at a certain level. Does that make sense? Okay, so and by this notion, we can also kind of see that it sort of follows a greedy approach, right? Because it's picking the best one available at a given point. From there, let's look at let's look at how we can adapt the algorithm of BFS to get to DFS, given this understanding. So I'll share my screen here. Yeah. So this is a algorithm for, we know about breadth first search, right? If you're given a source node, target node, we typically use the data structures visited set and a queue, right? Visited set mainly to track that we don't go into cycles. And we use queue because we are doing level order. So it's a pretty straightforward one. We start from the source node into the queue. While queue is not empty, dequeue the element, mark it as visited. If it's a target, we stop there. And that is, we'll see as we go in another examples, how that is an important differentiation factor between BFS and Dijkstra. And if it's not a target, then we just explore the unvisited neighbors of B and keep adding them to queue. So given this algorithm for BFS and from what we just discussed about Dijkstra, that we have to account for the edge costs and we have to process our queue in such an order that the cheapest path is processed first. So given that kind of understanding, do you see how we can adapt this algorithm? Like where would this need change?
Yeah, one question actually.
Yeah.
Shouldn't we mark this node visited inside whenever we are traversing it in unvisited in this for loop? I mean,
Uh, where do you mean?
in this for loop, else wala for loop. I mean,
Oh, um, okay. So you're saying Mark V has visited here. Would that?
add to queue and mark visited.
Yes, I agree. We should mark visited here.
Because I think this can impact the time complexity of the algorithm.
I think this algorithm has a trick to mark it visited when you remove it.
Which is what I was doing, right? When I'm removing.
So I think that was correct. When you explain, it will come
Okay.
visible. That algorithm has. I think you can comment that for now. We can come back there.
Okay.
Okay.
Yeah, but this might be good discussion.
Yeah, you can comment that for now, but
yeah,
the algorithm has a trick. When you remove, then you visit it, and that will become evictable as soon as you show example.
I see. Okay, cool. So maybe then we can just take an example here. Let me just go back to the previous one. We have A to, not the best way to draw, but is there another one? So I'm thinking of this graph, the same one that I was showing, the squared one. So A to D, the cost is 100. A to B.
It's directed graph?
I mean, it shouldn't make a difference because we are tracking visited, but we can think of this one as directed.
Okay, fine.
Fine, yeah. So so if we have a graph like this, do you want me to go over BFS quickly or? Let's just quickly go over it. It's not going to take time, and we are going to talk about that visited aspect as well. So if we are given a graph like this, and this is that square pattern that I was showing. So in breadth first search, given my implementation here, we are saying the visited node is visited list as 0, is null in the beginning, and your priority queue is, oh sorry, your queue is and the way we traverse is that we take out A and we put it in the visited list, and then we add its neighbors, which are B and D, right? And then I'm just going to revise this. So if you have questions anytime, feel free to just raise your hand. And then next we revise, we DQ B, and I add it to my visited set. And remember that my target is D, right? So source is A, and so now when I DQD, that's my target, and that kind of, I can track the path using a map, and that tells me that I can just go from A to D. That's my traversal for breadth first search. So do we want to, let's first quickly go over the idea of its difference from Dijkstra, and then we can come back to this visited because I also highlight the Dijkstra. So anyone has ideas on how we can adapt this algorithm to map it to the concept of Dijkstra?
So
Use
basically,
a priority queue or like the minimum neighbors?
yes. So basically, when we are removing something, so if I'm getting in some way the shortest, closest person to me, that will solve my purpose. So then we can think about some data structure which can do that.
Right. Yeah. So, so essentially, what Asim and Naga are saying is we want to focus on the closest path, right, amongst the ones that are not yet explored. So we are going to keep track of, in this case, since the edge cost was always 1 or equal, we didn't care about that. But in case of Dijkstra, we need some way. So if you will go back to this algorithm, here I see there are 2 points which are kind of important for Dijkstra. One is this one, that when you are enqueuing to the queue, you also want to enqueue the cost, right? You want to compute the cost of the node. Plus, you want to enqueue based on that, essentially. In other words, we need to refine our queue such that it reorders or it enqueues the elements in such a way so that the cheapest one is processed first, right? So if I take care of this, then when I dequeue, I'll be following a certain priority, right? So in this case, going back to our same example, here, if I'm following Dijkstra, I will do start node is A, and when I take out A, I will say I'll also attach the cost to my neighbors. So which is D. Now, given that it's a priority queue, we're going to use some comparators or some evaluation which will let me compare the cost of nodes which are available in this list and pick the cheapest one. So in this case, the cheapest one is B, and that is why that gets picked. And now from B, you can go to C, which is what's the cost to get to C? So my start node is A. Is there a way to?
It would be 22.
It will be 22, right? Like A is the source node. So I'm going from B. So cost to get to B, essentially what I'm saying here is, what is my cost from B to C? That will be equal to cost from A to B, or from source to B, plus.
Do you mean A to C? Cost from A to C.
Yeah, A to C.
Yeah, I mean, I was just trying to, like in this case, essentially we are trying to do this, right? But yeah, it depends on how we want to say it. Yeah, source to the node under evaluation. So this will be like starting from source, where am I coming from, right? Parent of B, parent of C is B. So I'm saying that first I have to get to B and then B to C, right? Which will which will be equal to 22, right? So now I have to pick from 100 and 22. So the cheaper one is 22, and I will and now I have D, and now my cost from C to D essentially is, even though it's 15, but I have to compute the cost from A to D via C, right? This would be cost from source to C and then C to D. So this will be like 22 plus 15, 37. And now, so this is saying I have, okay, so here's the thing. So this is also cost of D, right? So I already have 100. So I can actually, when I compute this, I can just update this, right? Is everybody following it? I'm not writing in a best possible way.
Can you please a little bit scroll down? I think. Yep, thank you.
So what I was saying is we have a cost already to get to D by as 100, but now when we evaluated this new one where we are getting to D again, but via C this time, the cost comes out to be 37. So now we know that we have a better path to D, which is 37, and we process that one. So yeah, so the final cost comes out to be 37, and the path is A to B. And we'll go over another like detailed example. This is a very like.
But this also explains if we have made D as visited earlier, we haven't put that again. So we have lost that A, B, C, D path.
Say it again, Asim. So you were saying if
basically you remember where we commented things.
Yes, yes.
So this explains like why we haven't made that visited.
Oh, okay. because we have an option to find a better path. If we would have
Yes.
marked it visited, then then we can't update it. Then we just
If P
assume
is
that.
already visited, we would not take C today. We only want
Correct.
to take
Yes.
or other way, if we want to make it visited there is another trick. We have to search that D node in the heap and update its cost.
Okay.
Yeah, one question. So basically, in Dijkstra algorithm, I agree that we will have to make it visited while we pop it from the queue. But when we are applying simple BFS, that time we can mark it, I think, here only, right?
Yes, that time we mark it here. It again depends. Like I've seen modified versions of BFS where you want to do some other trick. Basically, when you're taking something out and that time you want to take a decision, that could be then at the top. Otherwise, if you already took a decision while putting in the queue, then yes, mark it visited.
Right. So yeah, I think the way I'm seeing this is, you're right, Asim. Probably there are variations of implementation, and visited is essentially when we mark a node as visited, we are saying that we are done with this node, right? We don't update or like we don't evaluate it. So that is where the concept will come
So
in. But
basically, sorry to cut you.
no.
There are three concepts: unvisited, visiting, and visited. If you see the algorithm, when something is in the queue, it is visiting. When it comes out of the queue, it is visited. So basically, we're using that concept here.
Okay.
Correct. Does that answer your question?
Yeah. I got it.
Okay. Thanks, Asim.
It's unclear to me when we would take an item out the queue. In what condition we would take it out of the queue?
So in Dijkstra, we are taking out based on the cost. So for example, maybe let me take a little more elaborate example that can help.
I think if you take some 5 vertices with multiple edges.
Yeah, I have this example here.
Yeah, I think this is better example.
Yeah. So in this case, let's say we are trying to go from A to Z, right? And we have to find the shortest path. So the way I just
sorry to interrupt. Can you please zoom this?
Oh,
that will be better. Thank you.
This graph.
Yeah, that graph is little small. Look like.
Dippy, I think you can press F11 so it will become full screen.
No.
Yeah.
Okay. So we want to go from A to Z, and yeah. So we'll just go through the steps here. So we are maintaining a priority queue, right? And we put in the priority queue, we put the start node, and we have a visited list, which is empty right now. So the way I do this is, so I'll just put the nodes here. So we start from, so A is our source, so that's 0. And initially we mark this as like infinity. We don't know the paths to any of them. And the reason I'm tracking previous node is it also helps to actually capture the path. So we'll so now let's go through how it works. So we start from A, and so we take that out of the priority queue, right? And we mark that as visited. And now we, what are the nodes that I can reach from A? They are B and C. And what is the cost from cost of reaching B from the source, which is A? This 4 here. So in my priority queue, I am going to pass the node and its cost. Right? And I'm going to also capture its parent. So now we look for what's my cheapest one, which is C here, right? So that's why I next pick up C. And from C, where can I go? I can go to E, D, and A, right? Now A is already in my visited list, so I don't need to go back to it. So now I'll update the cost to get to E. So what is my cost to get to E from the source, but I want to go via C, right? So the way to look at this is we already know so far the cost to get to C from source is 3. So it is 3 plus the edge weight of C to E. And the way I got to E is my parent is C. So here in my priority queue, I'm going to add E as 13. So what would be the cost to get to D using this similar logic?
22.
Keep
15.
10.
Oh, 10.
10.
So there are a couple of answers, right? One is 10. Then
no.
somebody said 10, right? Any other, like I heard some other answers, but if there is a confusion.
22 I said. Actually, which node we have popped currently?
Yeah, so we are exploring C right now. We have, popped C.
Okay.
So we have popped C, and then we say that what are the nodes that I can go from C, and they are E, D, and A. A is visited, so we don't care about that. And then I'm checking, for example, C, and that's how I computed C. E, I mean A to D.
Then for D, it should be 10, I think.
It should be 10, right? So because I know that essentially read it as this one. I'm saying what is my, like the heading is saying shortest path to get to D from source, right? So which is, and here I'm exploring it right now. My node I'm exploring is C. So I'm saying what is my shortest path from source via C. That is essentially what I'm trying to do here. And I know the cost to get to C from source is 3 from this. And then if I look at edge weight of C to D, it's 10, it's 7. And I came here from C, right? So this I need to add to my priority queue. So which node will pick up next?
B.
D.
We'll pick B, right? That has the...
Yeah, we'll take B.
Yeah, because that's the least cost so far.
Yeah.
So this will be B. Now this is like another way of looking at the difference between BFS and Dijkstra. In BFS, if I start from A, at that time, I'm only evaluating B or C, right? And when I get to C, I'm only looking at E and D. I'm not going back to B. But in Dijkstra, we keep this list, kind of open, and we don't just focus on level, but we look at all the nodes that are available to us that we can possibly go to, and we pick the cheapest one.
Okay.
So
I have a question. Yeah. Why we mark C as visited?
Right. Anytime we dequeue from the priority queue, I am putting that in my visited one. So this is like saying that I know the best path to get to C from source.
But what if there is another path to C that is better? Right. And
we'll see that example. We'll see that example of, I think it will hit when we hit E. So, Leon, just to your quick answer to your question, the concern that we may have a better path, that is the whole idea of putting certain nodes, like how certain nodes stay in priority queue versus visited ones. So we'll see that we already know that this is a direct path from A, right? There is not really another path you can reach to. Let me just cover the E node, which will show the two different variations of path, and then we can revisit your question. Maybe that will help clarify it better.
Hello, I have a question. Like priority queue, it's given in the question, or we are deciding on which basis.
Yeah, so that's a good one. So the reason we are choosing priority queue is more to kind of improve the runtime and complexity. As you can see, if I just, let's say if I don't choose a priority queue, right? If I just am using a simple queue, then how are you, then another approach of following this Dijkstra is just doing a linear search. What's my cheapest cost, right? That will be like order of number of elements in the queue, correct? But if I'm doing a priority queue, we know that if we implement it like a heap, then the complexity drops to log of v. Did I answer your question, or was it you were asking?
No,
So what was
partially I'm satisfied. What are the parameters are we choosing B, E, D as our priority queue parameter?
Oh, so I am just passing the node ID, which in this case is like the node label, right? And the cost to get to that node that I know so far.
Basically, I guess like cost we are taking in priority queue, right? So
Yeah.
based on cost only, priority queue will work.
Correct. Yes.
I think so.
Yes. I'm just adding a node label to know which node.
Like if we will use only queue, then we need to like pop element from first only, right? Whatever we will insert first, we need to pop from there on.
Oh, that's true. That's another way. Yeah.
I think so.
Yeah, no, that's true. And the other point I was mentioning is, thanks for that, response. So you're right. Like when we follow queue, we are just doing that first in, first order, first in, first out. So if we just keep pushing elements in a regular queue, then we are not really taking into account the cost, right? That's point number one. The other thing is that let's say if we also want to tweak that, that's where the point that I was mentioning is coming into picture. If I want to maintain a queue without having a priority queue per se, then what I have to do is it's more like inserting in the middle of the, like the insert. If I keep queue as a linked list and I have right now only node with cost 4, and let's say 13, right? And now I want to add this node D, which is cost 10, right? Then I have to kind of, it's more like if I'm using an array, it's more like shifting and adding. So it's not like the regular order of, one operation to just fit it at the end.
Hey, Dippy, just one quick thing. So, Preeti, did that answer your question?
Yeah, I think the answer would be the shortest distance from A, the nodes will cover like that.
Thank you. Let me try to maybe explain it in a slightly different. This is how I understand this algorithm, right? So starting from A, assuming like you know nothing, you haven't seen the graph at this point of time. What is the shortest path to A from A? Cost 0, right? From A to go to A, 0. Very simple, correct?
Yeah.
Now from this point, what is the best thing you can do? Like let's actually find out all A's neighbors. So you have B and you have C. So so far the best way to go to B would be a cost of 4, correct? From A to B, you can go with a cost of 4. The best way to go to C is actually a cost of 3 at this point of time. But what is possible is that you may have an answer that actually goes from C to B with a cost of like say 0.5 or something like that. So B is not really 4, right? B can be anything. It can be 4 or it can be less than 4 or something like that, correct?
Yeah.
Yes.
So far, if you look at your candidates that you have right now, you have B is possible. I can go to B with a cost of 4. I can go to C with a cost of 3. Correct?
Okay.
Now, you pick the least one. So is it possible to go to C with a cost of less than 3 by doing anything else? It's impossible.
No.
Correct. The only way to go out from A, like, even if you had like more vectors pointing out, if you had like A to X or whatever, and those were greater than 3, the only thing you'll have, since all the edges are guaranteed to be positive, there is no way to go to C in any other way, which is like, cheaper than 3, because you have looked at everything you can go to right now, and C is the cheapest, and there is no way to come to C with any other way. So that's why you pick C. Okay. So now certified. So I know that A can happen at 0. That is done. You cannot make it cheaper than that. I know that you can go to C at cost 3. You cannot go cheaper than that. Those two are clear. Okay. Now what you do is you go look around and see where can you go from C. You can go to E, you can go to D, and you can, that's it. I mean, assuming you had a line from C to B, you could have gone to B as well.
Yeah.
And now what you do is you update all the costs if you have to update or add the cost. So what is the cost to go to D? It's 7 more than C, right? So so D should be 10, which is what she has in the priority queue right now. And what is E? E is 10 more than 3, which actually is 13, correct? So now with this information, what is the next node that you can go to? Like, you can go to B at a cost of 4, you can go to E at a cost of 13, and you can go to D at a cost of 10. Those are the 3 options that you have, right?
But for E we can also choose 12 now. A, C, D, E.
But we have
we can, but we don't know that yet, right? So far that's what we know. So what we know is we know B, we know E, and we know D based on whatever minimum information we have. What we know is B is possible at 4, E is possible at 13, D is possible at 10. That's what we know right now, right? So of these things, right, what is the most guaranteed thing? B is guaranteed to be 4. There is no way you can go to B faster than 4. That we know for sure, correct? So then that is what you process. You put a X on B and say that's what you dequeue, right? You're dequeuing the B and you're saying B is now done. There is no way I can make B faster than 4. 4 is the answer. Then you look at all the outbound edges from B. Right? Now
and I think
F is possible at 9 and E is possible at 16.
So,
but E was already 13. So there's no point. The BE edge is useless. So we just do nothing at this point of time.
Yeah. So
we
can
have to take for all the nodes, or the which is mostly connected to A. Sort of a confusion.
You at every step, what you will do is that you will pick the lowest cost that you already know of right now, because there is no way to make it cheaper, right? See, the one way to make the cost of D cheaper, like let's say you had a line between B and D with a cost of 1, right? I mean, you don't have to draw it, but if B to D was cost of 1, then you don't have to go to D at 10, right? You can actually go to D with a cost of 5, A to B and D is 5, correct? So all the other things in the priority queue can be cheaper depending on whatever edges you come up with new. But the top of the priority queue, the one that is actually at the beginning of the priority queue, right? The one that says that B is 4 right now, that you cannot make it cheaper because there is nothing else. So that is why you say that B is 4, that is for sure. I don't know about E, I don't know about D, I don't know about whatever else is in the priority queue right now. But the very first thing I know is guaranteed to be the right, like the best way to reach B is 4. That I know. So as you figure out the best way to reach B, you find out all B's neighbors and then you check if you have to update the priority queue or not. And you don't have to use a priority queue. You can use an array, you can use a hash map or whatever. But those like that arrays and hash maps will actually cost you more because you have to go through and iterate through the whole process and whatnot. Like priority queue is just a simple way to keep this information, because at all points of time you're only looking at the top, right? Of the queue. And I mean, you're updating the elements in the queue, but you're only looking at the top of the queue.
Okay.
And Preeti, to your point about we can reach E in a better way, we'll come to that. But as Vivek is explaining, it's like right now, since E is in our priority queue, there may be a possible better path. We are not saying that we have logged it to 13.
Okay, cool.
Yeah. One question I have.
Yeah.
So can we also discuss runtime of this?
Yeah. Let me just complete this walkthrough and then we'll discuss the runtime.
Sure.
Yeah. So we were at this point. So we are now exploring B, right? So we take that out of our queue. From B, I can get to F, E, and A. And A is already visited, so I don't need to go back to that. So for F, what would be my cost to get to F? Cost to get from A via B. This will be 9, right? I know the best cost to get to B is 4, and then B to F is 5. And here my parent would be. Now coming to E, what is my cost to get to E via B? It is 16, right? 4 plus 12. But I already know from my priority queue that I have a path with the cost 13, which is 13 better than 16. So I ignore that. I don't need to take this into account. And then A is already visited. So that's done. Next, what will we pick here? So we need to add F here, which is the cost 9. So which one will we pick next?
F.
We pick F, and what are my possible destinations, unexplored ones, which are not in my visited set? It's only Z, right? I have already B's in my visited set. Cost to get to Z is 16 plus the best way to get to F so far, which is 9. So it is 9 plus 16. And I got here via F, right?
So Dipti, you can go A, C, and D and E also. That is a cheaper, right?
Yeah, I'm getting to that. Yeah, right. So let's say if and that will happen when, so at this step now, right? If I'm just following the algorithm, now I'll pick D, right? And from D, we're saying that my neighbors are, if I look at E, what is my cost to get to E via D? It is 10 plus 2. Is that right? Yeah, right. 10 plus 2, 12. So I know I found a better path to E compared to what I had before. Earlier one had cost 13 and now it had cost 12. So if I update this to 12, so I say I have a better path, 12, and the parent here is now D. Is that what you were also saying? The question we just had? I don't know, somebody was pointing to that we can have a better path to E. Let me know if any confusions there. So now we found this was an example which tells you that we had to update a cost when we found a better path. So in this, now next node we'll explore is E, and from E I can get to Z, right? Which is not in my visited set, and the cost is 5 plus 12, 17, which is again better than 25. So I'm going to actually revise it, and I'm going to say this is path to Z is 12 plus 5, and this is 17. And this time I got to that path via E, right? And then this is my destination node. So I update Z to 17 here. And when I pop it out, I compare it with, at every point I'm comparing it with my target. So at that point, I know that the best cost to Z is 17. And we can see that the reason we were maintaining this previous node was to trace the path. So here I can say that, so essentially this is like I'm overwriting F. So I'll just, trace it back. So I'll say E, and then what is, how did I got to E? Best path is D. So is I'm tracing it based on this table and previous node. So I'm saying Z to, go from Z to go back to E. And then how did I got to E? The best path I know is via D. And the best path to D comes from C and C to A, which is my source node. So this is how we get the shortest path along with the trace. And the beauty of Dijkstra compared to BFS is the point that anytime when you're given a source and target, when you hit the target, you know that this is the cheapest cost, cheapest way of getting to that. BFS may not give you that. Does this example make
sense? I have a doubt actually.
Sure.
Yeah, so the contents of this priority queue, is it like a pair or how is it? Is it just the weight or are we?
Right. So I'm passing, I can show an example. So I'm passing a node ID and a cost of the node. So I'm keeping it as like you can think of, there are different ways of implementing it. So you can implement it as a tuple or a class object with two properties, node ID and weight.
Yeah. Okay, thank you.
I mean, one thing to notice is that it is a specialized version of priority queue, right? Because we are changing the priority when the items is in the queue.
Right. Yes. Yeah. We are updating the cost. We have to take that into account.
So yeah, there is a special data structure called index priority queue, using which we can basically, change the priority of anything that is already there in queue.
I know that. Okay.
Yeah, so that allows updates also. Yeah.
But does this walk through? Yeah, sorry.
Yeah, sorry. So otherwise, you can't basically update priority of, I mean, if normal priority queue when we learn or implement that, right? We can't update the.
Well, I was doing it, and the examples I saw, and the way I was doing it was, like I have a cost associated with every node. So if I'm having this data structure, if I have to update the cost, then I just update.
You update the cost, but then
I
you
see.
have to,
Yeah, it is indexed.
In priority, you have to move up and down, right?
Right.
If you outside of priority queue, you update the cost. It doesn't affect the priority queue data structure.
Okay.
Yeah. Okay. Go ahead.
Yeah, don't know if we can get around. I mean, like instead of implementing index priority queue, maybe team map might be able to give us least key.
I think I think what we can do is we can simply insert node multiple times instead of updating. So what happens?
Yeah. If we see already visited one, then we ignore, right?
Yeah.
Okay. And we'll see that example, and actually we'll see that notion in one of the problems, the cheapest path one with k-stops, where I think this idea is useful that you don't just, if node is visited, you don't just ignore it. You should keep, adding it to the queue. But yeah, that idea is also useful.
Or like maybe we keep hash map plus priority queue so that when we need to update it, we get to know whether that item is there in the map, so that directly with the map we have the node means reference, whatever is there in the priority queue, so that we can directly reach there.
Yeah, I was using the concept of array, like some distance array, and I was updating, similar, but there are variations as you are pointing out. Okay. So maybe let's, I think a lot of things that we are discussing, are also useful from the complexity analysis. Like there was a question before, why priority queue, versus a simple array or other stuff. So I think that's a good discussion, but I just want to first close on this example. If there are any questions on like how we walk through this.
My question is, in this case, I see that it worked because Z is the last node we visit.
Right.
Right. But suppose Z is not the last node we visit, then
yeah.
I have doubt.
So, yeah, let's quickly go through that, right? If let's say E was the last node, if we want to go from A to E.
Yes.
Right. So in that case, like when we got to the step that in the priority queue, we had a cost of 13 to get to E at one point via C, right? But then when we, I don't know if we want to go over it quickly.
But at that time, you after you done that, you put E in the visited set, right? So that means
no, the point at which we put a node in visited set, essentially we are saying that that will only happen when we get the cost 12 evaluated. And we can quickly look at it. So we are not, any node is not going to move to visited until we have, until we know the best cost to it so far. So let's quickly, just for clarity, let's quickly look at it this one, right? So if we are going to E, we have B and C first, which are cost of 4 and 3. And then let's say, so I'm exploring C at this point, and the cost to get to E there is 13, right? And we can also get to D, which is 10. And then we pick up, I have to write it down, it's a little confusing otherwise. So we have explored, let me just erase this. So I have A in my list and I got B for, then I explored B, then I explored C, and that gave me of 13 and D of 10, right? Now, when I pick B now, I know this is not my target. And this is telling me that this is the best cost I know so far. It may not be the optimal one, but this is the cost I know so far. When I explore B, I get the cost of E as 16, which is not any better. And then I get F, which is 9. And now when I explore D, sorry, but when we explore F now, we are getting Z, 25. So you see here, the point I'm trying to make is, if your target is E, we still know based on this our state so far, we haven't reached the best possible cost yet, since it's still in our priority queue. Now when I pick up D, D is not my target, and the D neighbor, now I'll get a better path, right? E is updated to 12. So in this case, I'm going to update my priority queue to 12. And that's where it stands. Now, the moment I dequeue it, that is more like the way algorithm works. It guarantees that this is indeed the best path. And I stop here. And now my cost is 12. I think this was a question by Leon, if I, right. So do you, or was there someone else? But I mean, does that make sense of how this idea of nodes in the priority queue versus visited is kind of important here to guarantee that anytime we dequeue a node, we are essentially saying this is indeed the best cost to get to that node. yeah, please feel free to, ask if something is not clear.
And one question, like, if there are negative weights, will this case would be handled? Means how will that?
No. So that's where the Bellman Ford will come in, right? That's
Okay, yeah.
specifically, so this algorithm is only for weighted edges and positive weights. Yeah.
Okay.
Which algorithm will get used when negative weight will be there?
Negative weights will be the Bellman Ford algorithm. We'll be covering that as well.
Okay, thanks.
Can you explain with index priority queue?
Index. Sorry, go ahead.
No. So you go ahead. I am not clear.
So index priority queue can be a different topic. Actually, it is a little bit bigger than. I mean, we can't cover this with the graph, so we might consider doing another session on that.
Okay.
Yeah.
But maybe.
But I can give.
Yeah.
I can give you a pointer from where to get the idea about it. Probably I'll put in chat.
Yeah.
Sure. Yeah, thanks. But any questions on this, like about if we didn't choose D as the target, choosing E, and how we got to the best cost?
So where are we storing the traced path? Means in the us we have to print the path. What will be the shortest path?
Yeah. So the way I have been doing this is like I was using a hash map. So with every node, like I'm tracking its parent, right? And then when I have to at the end print the whole path, I essentially traverse that hash map, and just the way I did here, right? From F, I'll go to B, and then I look in the hash map, the node with key B, and get its value, like that.
Okay, so every node will be having its parent, so it's a key value
Yeah.
pair. So that
Yeah.
we can trace that.
Right. Like I was using a parent map of node, comma node.
Yeah. Okay.
So if that's clear.
So this is the only way, or we are going to discuss this minimum heap also.
So what I noticed, I'll show you an implementation I tried, which was before I started using priority queue. There, I was just looking at, I was just using a linear search as a very brute force way. It's of course not the right, like the, it doesn't compute it in the best time, but I was just using a linear search to find the next element I can explore based on the minimum cost. And that was like order of number of vertices, right? In my queue.
Yeah.
But priority
Connected
queue is,
vertices.
yeah, priority queue is better. So that's kind of the,
Can we talk about complexity?
Yeah, I think that would be good actually.
Yeah. So let's, okay, last call. No, this is good, right? Or any questions? Okay. So let's talk about the complexity, right? What we are, if we go back to this pseudocode, what we are doing here is when we are exploring a node, for every like edge of the vertex that we are exploring, we are actually computing the cost of its neighbors. And then in some way, if we are using priority queue, then behind the scenes, like it is kind of rearranging it so that it's inserted in the right order, right? So the way I look at this is the complexity will come from, one is this section, right? When I'm enqueuing a node. And then anytime I'm dequeuing, then my priority queue will be, adjusted. So my analysis of this is, so for NQ operation, and here I'm considering priority queue, right? So how many NQ operations I'll have, that will be based on this thing here. Like as many edges I have, as many outgoing edges I have for a given vertex, that will define, and if I see like P for edges, and then I'm saying that since it's a priority queue, and that will be like log complexity, right? So my my NQ operation, I'm looking at it as E log V, and then my DQ operation is also happening for each vertex in my queue. Every time I DQ it, it log of that. So the complexity of Dijkstra would be
Sorry, why DQ would be V log V?
So DQ is like given that it's priority queue, right? Anytime you pop the the minimum element, you have to rearrange your the heap, right? So which is log V operation, and V, the factor of V is accounting for what is the maximum number of elements you can have in your priority queue at any point. Given that, for example, if you have a fully connected graph, thinking that would be like the number of vertices, like V, probably V minus 1, I think, because if you're
No, that's
exploring
fine.
the vertex. Yeah.
That's fine.
Okay,
I think
one question.
Yeah.
Go ahead. Yeah. So, basically, I think we are exploring edges, right?
Yeah.
And so if say we have set 10 incoming edges to one vertex, then we will be adding that vertex 10 times in the priority queue, right?
So yes, so I also had the same comment.
Yeah.
So
So how do we be sure that priority queue size will not go more than V?
No. So the thing is, for example, we saw in the example when we got to E here, there were like the in degree of E was 2, right? But like we didn't get to add it twice, at least in this implementation. Like I think there was a point where we were saying we'll keep adding.
Actually, this example was the trivial one actually. So that's why it
no. I think let me get to that answer. So we are using index priority queue, in which if E is already there, we update its priority rather than adding.
Yeah. Yeah.
Okay. But if we I think in a discussion we were saying that we can simply add E as many times as we want. So in that case, the log whatever the complexity we calculated, the log V will become log E, because for every vertex we are going to add, so in that case it will be log E. Yeah.
Which I just joined. Which algorithm we are doing? Dijkstra or
Dijkstra.
Okay, thank you.
Does that answer that question?
Yeah. So it will be E log E then.
If we use index priority queue where we can update the priority of the vertex, then it is E log V.
Yeah.
If we don't use index priority queue, normal priority queue where we keep adding a vertex rather than updating the priority of existing vertex that is already in the queue, in that case the complexity will be E log E.
Okay, got it.
Yeah, because that many, we will have duplicate.
Yeah, thanks. Actually, that was a good point.
Yeah. Somebody raised a hand. I think Preeti. Do you have any question? Some time ago.
Yeah, I have a question actually, but I'm asking that initially when we are using hash map, so we are choosing the nodes according to the distance with the neighbors, or
so where are we talking about? Can you like hash map? So we are using hash map in this example for the tracking the parent, right? But we are not using hash map for any like.
So for distance or to pick the next best node, we are using priority queue.
Yeah. So Preeti, there are like, if we talk about data structures, in this example, we are basically in this algorithm, we are having a priority queue, which is helping us to choose the next node to explore. And we are keeping the cost of the node there, cost of the path. And then we are using a hash map for actually defining this path, right? When we get to the destination, then how do we print the path back? That's the only purpose of hash map here. It's not accounting for any cost. Yeah.
Okay. Thank
Yeah. And of course the visitor list. Yeah. Does that answer the question?
Yeah.
And also, yeah. Okay, cool.
Do we need the visited set here? Visited array set? Because we are visiting the node again and again to reduce the cost if it was visited earlier.
No, not necessarily, right? Like when we got to, for example, B, like if A was the source, we got to B. When we are exploring its neighbors, right, we tend to ignore A because it's being visited. We know the cost to get to A is, we have already.
But in the example, if we start ACE, and then again, we are visiting ABE. So it was already visited, but if it has a lower cost.
No, so when we explored ABE, at that time, E was not in our visited list. E was in our priority queue.
So visitor list is the one where, once it comes out of priority queue, then we will never want to see that again. Right. If there is another vertex is also coming, suppose there is, so we start with A, right? Now any vertices that going to A again from F or E, we are saying that A is visited, so we are not never gonna do anything with that path. So visited is required, otherwise we will keep redoing it, right? How we know that at what point we need to end? Otherwise we have to go through our whole map.
Exactly.
Okay,
so in the example that you just gave about ACE and ABE, if you follow this algorithm, you'll see that until we have explored ABE, right, E hasn't moved to our visited list. E will still be in our priority queue. I mean, maybe you want to just, quickly try it out and see it for yourself, but that's the idea, that moving the nodes between priority queue and visited.
So E was not in the visited list just because E's values was not the smaller one. But what
yeah, sorry, go ahead.
What if in any example E's value will be the smaller one and it will be clashing in an example maybe? So is it true that E's value will be smaller only then we will put it out from the priority queue and enter it to the visited array or maybe visited hash map?
So I'll put it a little differently. I'll look at it as, let me know if that kind of answers your question. I see that the moment I put a node in visited, there is no possibility that I can get to that node with a cheaper cost from what I have discovered when I put it in my visited. Is that
that would mean all the in degree to that node that already processed, right? Any node that reachable from this given node already processed, so we can make the decision.
Any node which is reaching this
so
node.
In this case, for example, let's say before we remove E, we have to make sure that we process Z to E, B to E, C to E, and D to E already.
Okay.
No. So one correction. So the moment, so the algorithm works that way, that the moment you take out a priority queue, you will not have any other shortest path from any other node, because it's either, so suppose there's a path, right? B to F to Z and E is also path is there, right?
I got, but I think in the priority queue, we will have the multiple instance of the same node with the different distance, right?
No, that is the variation we are talking about, right?
Yeah, I mean,
variations
either
to this. Yeah.
We can either have that or we can update it.
Okay.
So either one, but the idea is that suppose we take the E out of priority queue, right? Now there is another path to reach E from any other node, right? Since we are talking about saying that the cost is always positive or zero, we are not talking about negative cost. So if any other path also exists, it is never going to be lower than the path we take out.
Why is that? I didn't get that part.
Because we said that the cost is always 0 or positive. We are not talking about negative
But
cost.
if we are choosing the different paths with this.
No. So yeah. So let me, maybe add one point there. So when we take the node out of the priority queue, at that time we are saying that we have explored all the possible paths to get to that node. And for example, in this case, when we went from ACE, the cost was 13. And when we went from ABE, the cost was 16. So there was another path to E, but it wasn't better than what we had seen.
But if we started from ABE first,
right,
and then we explore ACE, then what
exactly.
happens?
Yeah. So let's. So if we start with ABE, the cost is 16. And when we, so that's the nature of algorithm, right? We'll never take out, let me just quickly, it's easier to explain that way. So if we go ABE, we know the algorithm will proceed in such a way that, but what will be the next node that you'll take out from the priority queue? Let's look at this. So you will have, your priority queue will be having E with the cost of 16, right? And you're also going to have, E is 4 and C is 3, right? And then in your, then you take out C and you got the cost of E as 30.
Yeah,
so
but if the cost of E, if we reduce it to...
Yeah, let's say if we make it, I don't know.
4, 16, 3. Make it 14.
Which one?
That C
This
to
one?
E. Yeah.
C to E. So if it is 14, so then it's 17, right? And we have explored, and then we'll also add D, which is 10. Now, by the nature of it, let's say, so we still have a path to E, which is better. Now we'll explore B. We won't take out E out, right? We'll explore B, and what is the path to E? There is a path to E, right? From B, and E is still not in our visited set. We haven't still logged it. We are not saying we have found the best path. So from B, we know the path, there's a better path of cost 16, right? At this point, one of the variation of algorithms is update this.
Okay.
Right.
Yeah. All right.
When
if we are updating there, then it's fine. Yeah.
If we are not updating and we are inserting, that also works both way.
Yeah,
Suppose we insert another node with the E, let's say 60.
Yeah.
Now we are going to take out D and we are going to get better E.
Yeah.
So in this case, the better is through ACDE.
Yeah, got it.
Yeah, okay. So So the moment we take out any node from that and we mark it as a visited, we can ensure that all other paths are either costlier or same. Because all other paths can, suppose B to F, F to Z, and Z to E is 0 cost, right? So that way.
Yeah, that makes sense now. Thank you.
There was somebody with a question. I think somebody raised a hand.
So what if the cost are like same?
I'm sorry?
Cost is, yes. So that is a good question. The thing is that suppose there are two paths and cost is same.
What if the
that is an arbitrary decision.
Yeah. So you can't guarantee saying that you can always get one path. It's all depend on your algorithm. Suppose A to B to E is same and A to C to E is same, and A to C to D and E is also same, for example. You can get one of this path. It doesn't matter because your thing is, your goal is to find the minimum path. And if there are all three same, you can return anything.
And if there are two nodes, like when you're running through this algorithm, if you get two different nodes, let's say I had A to B 4 and A to C also 4, right? In that case, it's just a random.
Okay, thank you.
So the edge case for this one is like, from A to B to F, and every other node are 0. The distance, are 0. So there could be multiple paths from A to E, right?
Then we can choose any path, right? If it's
yeah.
yeah.
But we still need to run through the R, I mean, we have to visit our node.
We can run till we all the nodes are visited.
I missed the last part. So, Bhavesh, so I think the question was that if node edges like weights are 0, like multiple node edges are 0.
Yeah, if all the edge, the weight,
Right.
are 0, then
Suppose all the numbers are 0 in this graph.
Yeah.
Right.
Then it will be like essentially then we are doing sort of a BFS, like all edge weights are same.
Yeah, but I think we will run the same algorithm also. It doesn't change anything. Right?
Well, it can. So Bhavesh, like if all the edge weights are same, then in that case, we can a path A, C, E, Z and A, C and A, B, F, Z is equivalent.
Yeah, both are same. Yeah.
Right.
I mean, it doesn't change anything in algorithm, I'm saying.
Yeah, sure. In the algorithm walkthrough, nothing will change.
I think
we
should move ahead now.
Yeah.
Yes, I think that's a time check.
Yeah.
If there's no more question, we can also take question later. But if the concept is clear, then we can move ahead.
Yeah. So next, I wanted to actually show one question, which is relatively builds upon this, and then we can pick a little more complicated one. So this is a question from Leecode. Everybody can see my screen, right? With the Leecode question.
Yes.
Okay. So this is this question is about that you are given a source node and you want to find the time to get to all the other nodes in the graph, and you want to find how long will it take for the signal to reach all the nodes, right? So in this, and if for example, there was another node 5, which is not really connected, then you will return -1 because there is no way that you can reach to 5 if it's not connected to this, any node in this graph. So then, so we can take this example. So this is just representing the graph, the first section. So from 2 to 1, we have a weight 1, 2 to 3, and so on. We have 4 nodes, and what was so this is our source node. So we want to send a signal from 2 to all other nodes in the graph, and we want to find what's the how long will it take, right? So in this example, we can see that from 2 to 1, we can send in like 1 unit of time, 2 to 3, 1 unit, and 2 to 4 is 2 units. So if you were to output the result of sending it to all nodes, it will be 2 units, right? Because these ones will be encapsulated within that 2 seconds. Make sense, the question?
Yes.
So, so this is more like, rather than saying a source node and a target node, in this case, you have to ensure that you can reach all the other nodes in the graph. And yeah, so there is, in the interest of time, since we also want to cover other questions, this is a fairly basic implementation of Dijkstra. So I'll just go over it, and then we can look at.
Are we covering other algorithm also, or only Dijkstra today?
No, we do have 2 others, but I don't think we'll have time for both of them. So
because in the chat they're saying to move on to the next item.
Algorithm.
Yeah, I don't know. Like I'm just checking because in the chat people.
Yeah,
are
I
saying
think the item was about moving from the walkthrough we were doing of the example.
Okay.
But maybe I can just go over this example and then we can go to the next one. So one of the things I have found a little challenging, and that might be a good learning for all of us here, is about even as simple as graph representation. And there are different variations. When you see online, you'll see different variations of how people are representing graphs. So in this case, I took this idea of using a class for edge, right? Source, destination, and the edge weight. And the idea is pretty, so there's one thing I want to highlight here. So I start with initializing. So I'm maintaining an array distance, which is saying distance of node I from the source, right? And I'm initializing it to like the max value in the beginning. And the distance of that source node to itself is 0. So that's what this is. And this is just my visited set. I'm initializing everything to false. And so this is one thing I wanted to highlight, and I'll post this solution on Slack, but just to highlight this point about priority queues and that implementation. As you can see that what I am doing here is just a linear search. It's not even a priority queue. So I am just going through all the nodes, I have
But
so far.
you are doing the minimum distance call, right? So it's the
Right. Oh,
so
sorry.
that is the priority queue part, right?
This is no, yeah, but I'm not implementing it as priority queue in this example. I'm still doing this simple for loop. So this is like order of n here. This is not a priority queue implementation. So this is what I was highlighting, that if you look at priority queue, it's actually helping you improve the complexity to logarithmic time. But if you do a naive approach, you can always maintain an array, right? With all the unexplored nodes in your array with their cost. And you can just keep doing a linear search to find what is the minimum one I need to pick next. And you just return that. Right? Like every time I add nodes to my queue, which can be implemented as an array, if I have 3 nodes with the cost 10, 20, and 30, priority queue is helping you identify the cheapest one. But if I just keep it as a plain array, all you need to do is traverse the array, right? All elements, find the minimum element.
So is this the array of array? For each node, we have the multiple entry and we have to pick up the minimum one, right?
No. So this thing, I'm not doing that multiple, I'm updating the node cost. I'm not keeping the multiple entries for the node. So remember, like we talked about how we can have different implementations.
Yeah,
so either anytime we revisit, we come to a node which has a better value cost to it, we just update the cost. So I'm using that algorithm here. I'm not, keeping duplicates.
But how you are traversing if we are not using the that breadth first search like Dijkstra or whatever? Because we are going.
I'm using Dijkstra only, but I'm saying my implementation of
Okay,
identify.
got it. Yeah. Then fine. Yeah.
Yeah, that is the.
So traversing is still BFS.
I think this is the basic Dijkstra, what she's trying to show, and the priority queue was the more efficient way of
Yeah, got it.
Yeah. So it's not BFS, still Dijkstra, but a little naive implementation. So this is where I'm updating the cost, right? If I find a cost which is better, I'm just updating the cost.
Yeah.
So we can, this was the one thing I wanted to highlight, that, if in the interview we don't know really this priority queue stuff, I think it's still okay to highlight that you can do this and then improve on it. So does that make sense?
Yeah, that is good
approach. Okay. So that was this question, and I can share the solution there. The other question was, it's probably I can at least show it. It's a logged one, but we can go over live here. I don't know what people would prefer. Do you want to go with this question, or would you prefer the next algorithm?
I think we will not have enough time with the discussion to again understand a new algorithm.
Okay.
If we are okay, can we do another session with the new algorithm?
Yeah, we have 2 more. So.
Okay,
Yeah.
What are the other 2 algorithms?
Sorry,
A star and Bellman Ford.
A star and Bellman Ford.
I think yeah, it is complex. I mean, it will take some time, right?
Yeah.
Bellman Ford, so it's better. I would suggest that we can schedule it for next week if possible. Yeah.
Okay, sure. So this was the other question, and it's a my observation of this whole section, right, of Dijkstra and shortest path is if we know the concept and the data structures, I think that is good enough for the interview, and we can build on it. I'm not saying we won't get complicated questions. We may have some tweaks like this one, but it really helps to understand the fundamentals of how it works. So this question has a little, has one constraint on it, which is that you are given a flight network and you want to find the cheapest flight from a source to destination. But the constraint is within k stops, right? So in this example, you want to go from 0 to 2. And if you're allowed that you can have maximum 1 stop between these, destinations. So your cheapest cost would be 200, right? Because you are allowed 1 stop. But if you're saying that you're not allowed any stop, then even though you have a cheaper path, but your answer would be 500, right? Everybody understands the question?
Yeah.
Okay. So what I want to do is I want to cover few approaches before stepping into the code. So anybody has like, how would you go about it? And I would encourage like not to think from like how we can optimize it. Like when you get an interview question like this, what's your first thought and what's your approach like?
Basically looping over the k and finding out the destination. If the number of node in between is more than k, then will exit that loop and go for the next one. Like for example, when there's a k is equal to 1, and we are starting from 0 and traversing to 2. So first loop we are traversing 0 to 2 and 0 to 1.
Right.
But as soon as we reach k with the number of
So you're keeping track of the stops, right?
Yeah, stops, yeah. But when we go for k is equal to 2, then we will take the result of the one stop, and then the second one, we will count the node. As soon as we get the cheaper cost with the
stop,
we will update that.
Mm-hmm.
Right?
So I think what you're saying is, you have you highlighted one key point about keeping track of the stops, right?
Yeah,
And you also want to, as you are exploring this, so the moment we get this question, we have an weighted graph, and we want to find the cheapest one. So that kind of points to Dijkstra. And the point of k stops, as I'm not sure who was speaking, but the point was we want to keep track of the stops we have gone through so far. And one thing there is, sorry,
we need to reach to the destination in exactly k stops, or we can get
at most k stop.
At most k stops, within k stops. So this is more like you can, if I'm giving k equals 1, right? You may find a path with 1 stop exactly, but that may not be cheaper. There might be a direct flight which is cheaper. So you have to kind of keep track of 2 things. You have to keep track of cost, which we were already doing in Dijkstra, and you also have to keep track of the stops that you have seen so far. And in one of the approaches that I was going with, this is coming back to our discussion earlier that if you visit a node, for example, in this case, when you look at 0 is the source and you can get to 1 and 2, right? Now you have this in your priority queue, you have this node 2 with the cost 500 and you haven't encountered any stop. So stops is 0. But now when you explore 1, your cost to 2 is 200. So you should not just update it, right? You should actually add another entry for 2 just so that you can compare the stops and the cost. Does that make sense? I think this is what somebody was alluding to initially when you were talking about stops. Because with the second entry of 2, you will have a cost of 200, but your stop will be 1. So now your problem reduces to, okay, I have 2 ways of reaching 2, one with 0 stop, one with 1 stop,
And we
and
take
these
the
are my
minimum of all, right?
minimum cost, out
Yeah.
of them. And
Yeah,
and the other point to note is, let's say you had another edge going out of, I don't know, there was another vertex which was leading to 2, or there was another vertex which was going out of 2, for example. You don't need to explore. You can prune your search as soon as you reach k stops, right? Because anything further than that will add to the stops, right?
Yeah.
So if I'm going from, let's say, 0 stops here, then the moment I see 0 to 1 and 0 to 2, I don't need to really explore 1 because I know that it will be adding stops to my path and I'm not allowed any stops. Does that idea make sense?
So
Yes.
when do we, like, is it going to affect the way we are going to remove from the queue? Like this queue operation?
That's so it shouldn't yes and no, according to me. So we are still going to DQ based on the cheapest cost, but if so let me just share can I copy this? I'm going to copy the graph. Okay, and you guys can see the whiteboard and the graph, right?
We can just see the board, no graph.
Yeah, and then the text.
Yeah, just the text, yeah.
I was trying to copy the graph, but maybe I can just quickly draw it. Essentially having so I was thinking of this as if I have a priority queue, then as an example, if I have node 0, then I'm keeping track of its, let's say node 1, basically. So if I'm keeping track of its cost and the number of stops, right? But so I will still use the cost as the factor to pick up the minimum one, but I'm also going to use the stops to identify that if I need to explore more. For example, in this case, when I want to reach 500, right? And here the minimum cost is 100 for node 1. So I pick that out of priority queue. And I know that from node 1, if I explore anything further, it is only going to add a stop to my path, right? Whereas if I'm allowed like only non-stop flights, then I don't need to explore this and just ignore it and look for the next one, which is node 2 with cost 500, and that's my answer. So I'm using both the vectors, so as to say like cost and stops, but in different ways. Does that kind of answer your question?
Yeah, I think this question is little, I mean, I'm not able to think of the edge cases. Like, so you are going to remove here 100 and 0, but
Right.
what will happen if, okay, and then you will again put 100, I mean, 200, and then the stop will become 1.
Right, exactly. So here, what I'm thinking, this is like, okay.
So first we'll populate priority queue with the for 0 stop, and then 1 stop, and then 2 stop, and then 3 stop, right?
Yeah. Correct. That is how we are going to do. But yeah, exactly. But anytime we hit, like we already know we are only allowed 0 stops, then no need to explore more.
But then, so in the priority queue, we can only look at the peak, right? Like the top of
the
queue.
top one, right?
And if the top has more than the case top, then we don't, I mean, we just take it
No,
out
so
of
I
the queue.
no, so yeah, that's a good question. So I would still use the cost for the ordering of the priority queue, right? But anytime I pop the element out of my priority queue, I inspect its stops value.
Yeah.
So I'm not ordering my priority queue based on number of stops. I'm still using the cost to order it. But anytime I dequeue it, at that time I inspect my node and see what is my stop value.
Okay. And if the stop has like reached K, then we, even if you pop it out, we don't process it.
We don't process it, yeah.
Okay.
So that's one idea. I mean, what I wanted to do was I had 2-3 approaches in mind, but yeah, sorry, go ahead.
So this means that there are multiple answers. So that, I mean, multiple answers, but then we have to find the cheapest one only.
We have to find the cheapest and K-stop constraint. Yeah.
So I think we can save all the stops value in some 2D array and then get the minimum of that.
Yes, that's another, actually I wanted to start with that. So if I didn't even had this idea about pruning based on stops, my brute force approach was I'm going to just find all the possible paths to my target, and I'm going to use that hash map idea to actually, preserve my path length. So in this case, my potential paths were 0 to 2 with cost of 500, right? And then another path was 0 to 1 and to 2 with cost of 200, right?
Okay.
As a naive approach, I would be like, okay, I'm going to construct all of this, and then I'm going to iterate through each of my possible solutions. So this is like 0 stop, and this is like 1 stop, and these are the cost, and then I'll pick the minimum one. But we can easily see that it's kind of more space, complexity wise also, it's taxing.
So if we find the minimum, we just update that same.
No, we are not updating in this case. In this case, I'm preserving, like you see here.
Yeah, in this case, we're preserving, but in the optimized one you were mentioning?
Yeah. In the optimized one, yes, I can just update it.
Okay, yeah. That makes sense.
Another approach I was thinking, let me share and we'll.
Yeah.
So could we just make a change to a DPS, depth first traversal, like
I'm glad you mentioned that. Yeah, it's interesting. Like maybe I would like to hear your approach, because I was thinking of an adaptation of BFS, but if you have an idea for DFS, that would be interesting as well.
So in DFS also, because we have visited set to avoid the cycles. While we are going, we are going depth first. We are diving into the next level. We can always count how many stops we have taken already, and then go no further.
Right. Yeah, that is like similar, but yes, I agree with that. Is the pruning step we were kind of alluding to. Yeah.
Correct. And so within those steps which are basically which were not pruned, we can always find out what is the best. For example, so that we can put in a priority queue and just take it from there if it is ending up in G.
Right. So you're saying, for example, in this very basic one, if you were only allowed non-stop, then you start from 0 based on your depth first. You're going to 1, but now you don't go to 2 because your stops is like you can prune it. You don't.
No, that is one stop, right? So when you start with 0. So we allow one more stop. So you come to 1 and you take the stop to 2. So that becomes one candidate that get pushed to the 200 get pushed to priority queue. Then again, basically in the DFS, we will go. We don't go exploring from 2.
Yes. Right. Because your K is 1.
Yes, that is what we get pruned. Then we go back and we start with 0 to 2, which is the direct path, and then the 500 gets pushed into priority queue. Now we know that 200 is better than this, and there is nothing else to. So it is a two-step process. The DFS is basically finding out all the candidates which what should I say? It takes into account the pruning step to come up with candidates and populates the priority queue, and whichever is the winner on the priority queue, that is the answer.
Right. Yeah. That everybody sees that idea, I think. And I had a similar one for like BFS, but I think
do we need the priority queue in case of DFS? That is what I'm thinking.
Yeah, we'll have to keep that because we want to see, for example, here the 200 and 500, which one wins. Because it is a graph problem, we cannot foresee.
No, actually, that's a good point there. That if we keep depth first search, right, by just the algorithm, the nature of algorithm, we are maintaining also a stack, right? And then we are on the top of it, we are maintaining a priority queue to kind of optimize, pick the cheapest one. So, but if we use, for example, BFS, right, a customized BFS approach with a similar idea that you're explaining about DFS, then we don't need that additional data structure. We can just
even additional data in the DFS also. If we are just saving what is the current, and next time when we are hitting that same node, we can just compare that value. If it is lesser, then we update. Otherwise, we can just move back, right?
So we can get rid of the priority queue that way. Correct.
Yeah.
So we are just keeping the best till now and keep improving on it.
Yeah. So but that way we don't need that. Yeah.
With DFS, it could possible that you're gonna go back to visit a node you already visit on the previous DFS. So that means you might redo the work again.
DFS, because you have to go to till the end and then go. So whenever we need the path, I think BFS will be the better approach, because we don't get DFS is more intense, like aggressively goes till the leaf backtrack, right?
So the Rajendra was saying, like we can avoid using priority queue and just store the values. What if we had many paths with the same value cost, right? But the stops were different. So then you'll have perhaps another data structure to maintain that, right?
Sorry, could you please repeat?
So what I was saying, like you said, we can avoid in DFS using a priority queue for storing the paths, right? So in that case, you said you can just store the value of the path or the cost of the path, whichever is the cheapest one. But I'm saying if we had many paths with different key stops with the same cost, then we still have to have another data structure.
Does it matter?
Right, like if we had, for example, a node 3 here, 0 to 3 and 3 to 2, with the same cost hundreds, right?
So that
then it doesn't. We need the cheapest cost, right? It doesn't matter that we need the.
Yeah. But if we had the same cost for all of them.
Yeah, doesn't matter. We'll take one path, right? I
don't.
No, but if we have many stops, like if we have if we allow for 5 stops, but if we still find 3 stops, so why I'm not going to take the 3
that
stops?
is a different variation of the question, and this question doesn't talk about that one. That you need to have the minimum stop and minimum price. That is what you are probably talking.
No, but any stops, first the cost is important, right? But if my cost is same for all the paths, all the stops, so still I have to go for the one which is the lowest stop, right? Or at least I have to put all the stops, all the paths.
Part of the question, but if that is the requirement, yes, we can do that. What you are saying, basically, we can keep.
Yeah. So I think if I'm understanding this right, so you are saying that if I have k equals 5, then I cannot just like stop at like k equals 3 or something. I have to evaluate all possible paths till k5 and then find the minimum. Is that?
Yeah, that is true. But if the minimum cost itself is all of them of the same cost, like I have 200 for all of them, right? I have about 5 to 6 choices, right?
Yeah.
With different stops of $200.
Yeah.
So I have to maintain some data structure or something, you know, an array also, right? And I have to reiterate through it again at the end to find which is the optimal.
Right.
Because I have to say.
But why I didn't get that part. But when we have the
no, so I think what he's saying is, let's say in this, similar to what I have drawn, right? So if I have k equals 1, then my cost from 0 to 1 to 2 is 200. And it's the same from 0 to 3 to 2. That's also 200. So the
and also
point,
0 to 2 also direct one instead of 500 if I had 200.
Yeah.
Right. So I will always go for 0 to 2. But so I'll have to still maintain some data structure to have all the paths till the end, till I go through the each and every one in DFS.
No, I don't think you might need just one array where you can.
That's what I'm saying. If I have an array, but right here it is only 3 paths, but I might have many paths also, right?
But only one will succeed. Only one will be the best path for you.
Yeah, but the one which is optimum will come the last. So you'll have to still keep all of them till the end.
We can improve the existing one, just like we did when we were getting rid of the priority queue. We started taking one and then improving on it. Similarly, we can have another array with whatever segments. So that is where if we come across any other path which has less number of segments than the current one, we'll just update.
Okay. But then you'll have some more additional logic to that.
Basically, one more thing to improve upon. Yes.
Okay, makes sense.
Yeah, that was interesting. Actually, I didn't think of that one.
DFS mostly is very easy to write and less, I would say, it takes very less time to write, and mostly because of the recursion thing, it's straightforward also.
Yeah. I think in interview perspective, as long as we can kind of, explain why one versus other, in my experience, that has really helped. Even if we choose one algorithm and we decide to go with another one, but since the focus is on approach, talking through the approach really helps.
Agree.
So, yeah, thank you.
So, by any chance, do you have the list of questions which we can solve with this Dijkstra thing?
Yeah, so I was right. So I'll share a link. Vivek had shared a link for those, Dijkstra questions. So I'll share that.
So you can share on the Slack also all the list.
Yeah.
Thank you.
Yeah. And if I think we have like 6 minutes. I think Shashank has an implementation for this. We can quickly go over that.
Yeah.
To close on this. Yeah. So I can stop sharing and.
So how I approach is like whatever DP was discussing. So just I'm taking, like, let's say these are the ages given to you, like from 0 to which all destination you can go. From 0 to 1 you can go with a cost of 100, and from 0 to 2 you can go with a cost of 500. So this is the map that I'm creating out of it, which will keep track from which origin to what extent you are going. So like you'll have this is the map. From 0 origin as 0 you can go to 100 with you can go to 1 with a cost of 100, and 2 with a cost of 500, and from 1 you can go to 2 with a cost of 100. Hereafter what I'm doing, just I'm using a heap in which I'll push the cost, and initial stop will be a -1 and the source vertex. And visited this I'm keeping so that if I've already visited some city, I don't need to visit it again, just to avoid the loop inside the graph for that. So I'm popping your cost, stops, and city. The moment I popped, I'll put it inside the visited city that I've already seen this. Whenever you find that you have reached the destination, your city and your destination are reached, you return the cost. Else, if you haven't used all the stops, your stops is still less than the required number, whatever they have told, just go to the map, go to the city map, pick those what do you say, flight cost and the destination, and if that is not visited in your graph, just again recurse it, cost, flight cost, and increase the stop by 1 and the next city, else return -1. So you can, like this, like let's say initially we had stop -1 and 0 I posed. So 0 I'll pop, that would be the first city that I visited. So what corresponding to this, I'll go to 1 with a cost of 100, and 0 was your initial. So the next is like you can go from 0 to 2 with a cost of 500. Now minimum of them you just pop it out 100. Now again 1 you have visited. So you'll append next, once you have reached from 0 to 1, next cost will be this whatever cost you had previous plus 100. So 200 you'll put inside the queue, priority queue, and then again minimum of them you take it out since you have visited 2. So by that time you finished all your stops, or just return the city from there. I mean return the minimum cost from there.
Right, right. So Shashank, if you go to, can you scroll down to your that?
Sure.
So yeah, so this is the idea we were talking, right? We are still popping, dequeuing based on the cost, but when we dequeue, we are looking at the stops in case 1 here, which is what we wanted. So we kind of know this is our, and we know the destination is 2. So
Yeah.
So you were saying if we pop it out and if it's greater than k, then we're not going to process that.
Yeah,
right.
exactly.
So this is an example of k equals 1 that he worked with. Like he showed an example, but Shashank may be like what Leon is saying with k equals 0, right?
Yeah.
That will answer his point about once you hit 0, right? You don't need to explore 1.
Further, yeah.
Is that how you're doing? I don't know.
Yeah, it's like same.
Yeah. So, Leon, like to your point about if k was given 0, then when we popped 100, right, from the priority queue on line 46, at that point, we know that if we explore any further, it will only add the stop to 1, right? And we are only allowed 0 stops. So that time we can just prune it and we can ignore that.
Can I see that in the code?
Yeah.
Like,
Sure.
Are we doing?
So here the stops will not be less than k. So what will happen?
We'll return -1 in that case.
No. K is equal to 0, right? K is equal to 0.
Right.
And
your stops is -1 in the beginning, right?
In the beginning, I've taken as -1 here in the heap.
Right. And so to 2 with the 500, the stops is 0. and then with the one from 1
So
to
now,
2 stops will be
so one said he goes through this line 25, which is -1 less than 0, and he adds that to the 500 cost. Then when he comes next, then stop 0 is not less than 0, and then we just
pop
come
the
out.
the remaining element.
Yeah.
Right.
But if we are checking the city is equal to destination before the stop is less than k, because if we
No,
return,
so that city is a popped element, so we don't check it inside the priority queue. This is after popping it.
Can you scroll down a little bit, Shashank? I just want to see where do you return? Scroll up. Where do you return the value? Oh,
if destination, if that the city whichever you have popped out from there, if that matches to that of your destination, just return the cost associated with it.
Okay. So if we have multiple paths with the same cost, it doesn't matter. You just pick the first one and return it.
Yeah, exactly.
but is that it will give the minimum cost?
Definitely, yeah.
At most k stop.
So Dijkstra will always give the minimum, but I think the question will vary a little bit. This concern that we are having about multiple paths with the same cost, but if they are doing, for example, in this case, if 0 to 2 was also 100, right? And we were given k equals 1, right? So you are allowed up to one stop, and your path could be direct 0 to 2 or 0 to 1 to 2. Right? But in terms of cost in general, the nature of Dijkstra is that whatever path you get, it will always guarantee the cheapest. But this constraint about hops is something we have to play with the logic about what we are returning.
But he can actually have a custom comparator for that.
Right. Yes. Like if they're equal, then what to return.
Right.
Yeah, so if we can modify this test case with 1 to 2 as 400, that will make it 1 to 2 400. Yeah.
Will I change?
Can we change to?
Yeah, 1 to 2, make it 400. Yeah.
400.
Yeah, whichever is minimum, first minimum is returning.
So
yeah, I think okay. So
oh yeah, here we are not concerned about how many stops we take.
Yeah.
Right.
That's why we were troubleshooting so much.
Okay. I think so. We'll take the other two algorithms next time. But any questions on anything that's covered today? So the main takeaway is that when is Dijkstra applied with the weighted edges, and we use a priority queue to reduce the complexity to logarithmic time. And this example showed when we had to play with another constraint about number of stops.
If we have cycle, we can't apply Dijkstra, right?
What is it? Sorry.
Cycle, like from 0 to 2 again, 2 to 0. Like if it forms a loop, you can't apply Dijkstra.
No, you can, right? Because it's
You
always
can,
positive
yeah.
edges, so it doesn't matter. I mean, there is no way to come back with a cheaper cost once you evaluate a particular node. So with negative costs and Bellman Ford is where negative becomes an issue, not for Dijkstra because it's all positive edges.
And also, yeah, that's right. And it's a visited set also. We are keeping track of that.
What if you have a self-looping node with zero cost? Would that still work?
So if you have a loop that actually is of zero cost, right, then it doesn't change the shortest cost. Like you'll have multiple solutions and any solution will be fine. So what we will typically do in most cases is we will not go through that loop. And we will be coming up with the cheapest cost will remain the same regardless of if you go through that loop once or 100 times, and we'll probably not go through that loop at all. in most common algorithms. But
Because
it's a good point.
Yeah, sorry. Because we keep the visit note, so we're not going to visit that again, right?
That is correct. That is correct. So hey, it is 11:05. So I just wanted to take a few minutes to thank Dippy and Shashank for actually walking us through one of the algorithms. Now I know we promised we'll do three, but we'll actually, as Bhavesh mentioned, we will actually take the rest in the second session and see if we can cover both in the second session, or depending on how interesting they are, we might actually run these as two distinct sessions. I think it looks like there's a lot of value in going through the depth and exploring it. It's better to actually spend more time on fewer algorithms and learn it better. So I really appreciate the enthusiasm and the interactions that folks have actually shown. So what I'll do is I'm going to stop the live stream and the recording at this point, and but we can continue. Folks, if you have any questions or any discussions, like we can probably continue for 10-15 minutes. All right. Thank you so much. Thanks, everyone.
Yeah. Thank you.
Thank you.
Thank you.
I have
Yeah.